Just drying your eyes out. Just like...
So remember that bonus problem that I offered to you all about the surface area of the roof?
Yeah.
So no one turned anything in, which I understand. But that was based on a problem that I heard about that was given at MIT many years ago. You all ever heard about that problem? So this, I don't know what class it was, but the students were given an assignment to try and estimate the surface area or the area of the MIT campus. And so, different people were doing different things. People were out there measuring, and the group that got closest, what they did was they took a map of the campus. And so whatever the campus was, right? They took the map. And what they did was they cut the map out. They cut the campus out of the map. And then they weighed it. And then they took the map itself. They took another piece of paper that, you know how it has the little legend here that tells you, like each inch is, whatever, 2 miles or whatever. So they knew that the rectangular sheet of paper, they knew the area of that rectangle, right? So then they set up a proportion. So it was the area of this divided by its weight was equal to the area of that divided by its weight, and came up with it that way. Pretty clever.
The person outside is like trying to mentally save the grade. It's like,
okay, we move on. So, remember we started class, we said in Cal 1 we do the closed interval method first, then we do the local stuff. Here we started with local, and now we're going to go to closed. So we want to kind of have an appreciation for why we're doing it this way. So back in Cal 1, when we had a function on a closed interval, like this, what we did is we said, okay, look, we can find these points. These are our critical numbers, or critical points. And then what we can do is just evaluate the function here, here, and then at the two endpoints, compare those and be done. And that was pretty straightforward. But here, with functions of several variables, if we go and try and talk about a closed interval, we have kind of a different problem presents itself. So we first have to understand what we mean by a closed interval. It's not a closed interval anymore, it's a closed bounded set. So can you look at these diagrams here and see the difference between a closed set and that is bounded versus sets that aren't closed? So like this is a circle, right? We're talking about every point inside the circle and every point on the boundary. This is a square or rectangle, every point inside and every point along the boundary. Here we have a disk that we are not including the boundary. This is an open set. This one is everything except that one single point. That would be an open set. It's not closed. And then this one is, the box without the boundary. So we are going to be looking at trying to find the absolute maximum and absolute minimum of a function bounded on a closed bounded set, right? So this is our domain. So it's kind of like this picture here. When we cut this function off, the domain is on the ground, right? This is a closed interval from A to B. So we're talking about the domain here is everything in between, including the two endpoints. Because our surface lies above the xy plane, our domain is a closed bounded set on the ground, all right? So we're imagining taking some closed bounded set, mapping all those points up into the surface, and then trying to figure out the highest and lowest point of the surface. So I have a visual for that. Should hopefully help a little bit. Let's see here. Let me evaluate this real quick. Get everything back to normal here. Okay, so this right here, we are going to try and find the absolute maximum minimum values of this particular surface on the closed triangle with these vertices. So first of all, take a look at this. This is just that surface, not bounded at all. Right? That's just the surface just floating along in three-dimensional space. We are not interested in anything with that. What we want to do is we want to look at this triangle with vertices 1, 0, 5, 0, 1, 4, which if we look at that on the ground, right, in our domain, this is our vertices here. And what we want to do is take just the points in that closed bounded set and map them into the function. So here's the closed bounded set on the ground. All right? And we're going to bring in, here's the surface without any restrictions. And now what we do is we will restrict this function. I think I want to do right here. Yeah, there. And let me pull the surface out. So that surface restricted just to that triangle is just that green part of the surface. Make sense? Everyone see it? So we want to know what the highest and lowest points of that surface are. Well, just like we did in Cal 1, we can find those in Cal 1, right? Those are our critical points. We can find the critical points of the entire thing, right? So it's like, imagine if this kept going and this kept going. There might be other critical points, but we can identify all these, right? We're going to be able to identify all of the critical points on this entire surface just the way we did in the previous section, except that we don't need to calculate D anymore because we don't care if it's a local max or a local min. All we care about is where they are. So we will find the critical points, but then we have to deal with this part where we have to evaluate at the endpoints. How are we going to evaluate this thing at the endpoints if we don't really have endpoints? We have entire like curves, right? Or straight lines in this case. So the way we do it is this. We will try and break our region down into parts. So for example, on this one, I could look at just L1, just this line. Imagine taking points just along this line and mapping just those into the function. They correspond to that part of the green graph. Do y'all see that? Right here. These are just these blue line, this blue line mapped into the surface. So what we'll do is we'll kind of look at it from the perspective of almost like a Cal 1 problem now. See this line? It's kind of like this is now. And it's going to be some function bounded on a closed interval in two-dimensional space instead of three-dimensional space. And then we just kind of move our way around like there. I'm going to use that back line and see how that corresponds to the back side of this surface. You'll see that? And that, if we look at it from this perspective, you know, straight on like this is like a parabola. And it's on a closed bounded set, so we're going to be back in doing Cal 1 problems. So for this problem so far, just talking through it, first thing we're going to do is find the critical points the way we did in the previous example. But then we have to break down this triangle into 3 separate problems. Each problem is going to turn into a Cal 1 problem. And the last one, of course, we go L3. That's this edge. That edge mapped in here is going to give us that side. And so that, again, will be its own Cal 1 problem. And then once we go around the whole boundary, we compare everything and spit out an answer. All right? All right, so let's do it. That's a different example. Okay, so let's do the work for this one. So first step is let's find the critical numbers or critical points. So the critical points, we're going to take the partial with respect to x, which here for us is y minus 1. And then the partial with respect to y, which is x minus 2. And then when we set each of those equal to 0, we have a pretty clean solution, don't we? So our only critical point that we get is 2, 1. All right. So this is kind of like when we were looking at the Cal 1. This is the inside. We're trying to see if there's some points inside where we might have maxes and mins. We need to make sure this is inside though, right? So let's draw a picture of our domain over here. Our domain, here's x and y here. We go, let's see, 1, 0 is here. 5, 0 is here, and 1, 4 is there. All right, so there's our domain, everything in here. So is our point 2, 1 in there? Yeah, it looks like it is, right? 2 is like right in here, 2, 1. So that is a valid critical number. So we will be using that later, right? And we'll be asking ourselves, just like we did in Cal 1 when we looked on the inside and then we compared it to the endpoints, we're going to want to look at this plugged into our original function to see what its value is. So do you all want to do that now or do it at the end? It doesn't matter when we do it. You just do it now? Okay, so what is our original function's value at the point 2, 1? Let's see. So we plug in 2 for x and 1 for y. Let's see here. 1? Yeah. Okay. So when we plug in 2, 1, we get 1. We don't know yet if this is going to be the absolute max or the absolute min or neither one. This could not be at all, right? It could be happening on the boundary instead of here. But inside our region, this is the only point of interest to us. All right, now we move along the edges. So when we move along the edges, we have to label these, and you can label them however you want. You can start wherever you want. I'm just going to pick and go. So I'm going to call this L1, I'm going to call this L2, and I'm going to call this L3. I'm calling them L because they're lines. If they were curves, I might call it like C1, C2, C3. All right, so let's talk about L1 first. On L1, tell me about every point that you would be trying to plug into the function. What do all the points on L1 look like? As an ordered pair, what do they look like?
0,
Something is 0. What's 0?
y.
The y coordinate, right? So if you're on this line segment, your y coordinate is 0. And your x coordinate, well, it's just x, right? But that x is not unbounded. It must live between 1 and 5, right? So what we're saying is we want to move along L1. So we want to take all points that look like this with x between 1 and 5 and plug them into the function and see what happens, right? So let's do that. Let's plug these points into the function. What is our original function evaluated at those points that look like x0? So that means we replace all our y's with 0, right? And what does it turn into?
It becomes 3 minus x.
3 minus x, that's it, right? 3 minus x. Okay, we are now in Cal 1 because we have a function, right? Which really at the end of the day is a function of one variable. And that variable is bounded between 1 and 5. So now what we're going to do is do like the closed interval method for this particular function. All right? Make sense? All right. So I'm going to do this in a different color because I still want to make the connection that we have here to Cal 1. Essentially what I'm doing is this. I'm defining a function g of x equal to 3 minus x. And I'm looking at the closed interval 1, 5. And I'm trying to find the absolute max and min of this function. So to do this, I take the derivative, right? Set it equal to 0 to find the critical numbers. What is the derivative of that? Negative 1, right? So negative 1, but that's never 0. So we actually don't have any critical numbers for this function. So that means the only thing we have to do is test it at the two endpoints. So that means I want to check g at 1 and check g at 5. And what would happen if I check g at 1? If I plug 1 in here, I get 2. And if I plug in 5, I get negative 2. Does that make sense? Okay. So far, I mean, just right now, at this point, we know that this is not the global max or min, right? Because we already found 2 places where our function is going to be bigger than 2 and actually less than this, right? So corresponding to what we have here, here's what I know. I know that at f, when my x value is 1 and my y value is 0, I know I get a value of 2. And when when I plug in 5 for x and 0 for y, I get a value of negative 2. So this is just, again, me trying to make it look like Cal 1, but this is the Cal 3 part. It's really an ordered pair going into the original function. And we just got to do the same thing now all the way around. Okay? And at the end, we compare. So let's go to L2. L2 is a little bit trickier than L1. So tell me about all the ordered pairs on L2. Pardon? 1, 4, 5, 0. I'm not following you. Oh, okay. So like this is the point 1, 4. This is the point 5, 0, right? Yes. But what do, like if I pick a point off of this line segment, what do they all look like? We said along L1, all the y coordinates were 0, and x just floated back and forth between 1 and 5. But if I pick an arbitrary point on L2, what does it look like? Okay, so that's what this, so what you're doing is you're using the fact that you can find the equation of that line. The equation of that line is y equals, what did you say? Negative x plus 5? How are you getting that? Well, you go down, what? 1, 2, 3, 4, and you go over 1, 2, 3, 4. So the slope of this line is negative 1. And so if it's negative 1, to find the y-intercept, you're going to have to go up 1 over 1, so that should be 5, right? So this should be slope negative 1, y-intercept 5. So if that's what the equation of that line is, then what do all the points on that line have to look like? The x-coordinate is just x, right? And the y-coordinate is negative x plus 5, right? This is your x-coordinate. That's your input. Your output is always the negative of that plus 5. And do you have any restrictions on x if you're on that line segment? 1 and 5 again, right? Your x has to be between 1 and 5. So do you all see that all points of this form with x between 1 and 5 is going to allow us to basically move along this line L2? Okay, now we need to see how we can turn this into some function of a single variable. So what we do is we plug these in to our original function. So we plug it in here. We'll get f of x, negative x plus 5 equals, okay, 3 plus, what's x times y? Well, that's this times this, right? That's x, that's y. So these two multiplied should give you negative x squared. I'm going to put it in parentheses. Negative x squared, and then plus 5x. You okay with that? Not done yet, though, right? Then what? Minus x, and then minus 2 times negative x plus 5. Y'all follow me on that? Let me do one thing, just in case that's confusing people. I'm doing x times y. Y is negative x plus 5. I'll do it on the next line. So this is 3 plus x times y minus x minus 2y. This is kind of an interesting approach, right, to do this. Just kind of walk your way around. Let's see. 3 minus x squared plus 5x minus x minus, plus 2x minus 10. And let's just put everything together. We'll put it in descending order. 6x minus 7. So when all is said and done, if I want to move along L2, it really comes down to trying to find the absolute max and min of this parabola on that closed interval, which means we're in Cal 1 again, right? So I'm going to take the derivative of that now, set it equal to 0, and then I'm going to take the two endpoints and I'm going to plug them into the function. So do you all want me to do this again with the g? Was that helpful, or do y'all care? I'll stick with what I have, all right? I'm just keep doing it. So I'm going to define a function, let's use something other than g. H of x is equal to negative x squared plus 6x plus 7, no, minus 7. And we're doing this on the interval 1, 5 again. So we take the derivative of this, set it to 0, which means negative 2x plus 6 equals 0. And that gives us x is 3. So this time we actually do have something to look at, right? So what we want to do is evaluate the original h function at 0, at 1, and at 5. So what happens at 0? What does this function spit out? Negative 7, right? What does it spit out at 1? Oh, hold on. I don't know. Hold on. I messed up. This should be 3, right?
Yeah.
Yeah, okay, I'm sorry. I was like, wait a minute. 3's not in this interval anyway. I mean, 0 wasn't in the interval anyway. So I'm doing 3, 1, and 5 into this function.
Yeah.
Need to clarify? We're good? Okay. So what happens when I plug 3 into this? Negative 9 plus 18, so that's 9. Take away 7, that's 2. Okay. What about at 1? Negative 1 plus 6. So negative 2?
Yeah.
And then what about at 5? Negative 25 plus 30.
2 as well.
You should get negative 2 again, right? The negative is out front, remember? Yeah, the negative is out front. So you're squaring it first, then the negative.
Yeah.
So that's what we get. Now, in terms of our function, here's what these correspond to. This is f of something something equals 2. This is f of something something equals negative 2. And f of something something equals negative 2. Right? That's what these three are. Now, what are these ordered pairs here? What are they?
3, 2.
So we have to go back to this formula right here. Right? 3 is the input, and then the y coordinate is actually negative 3 plus 2. So this is 3, 2, right? And then 1, 1, 4. And then when we plug in 5 into that, we get 5, 0. So look, if I'm trying to illustrate what we did here, visually, we went into L2, and we were looking along the back side of this, really, and we wound up getting a parabola, right? You can see the parabola right there. And we found the points of interest to us were at, in the domain at 3, 2, 1, 4, and 5, 0. So that means it was at 3, 2, so 1, 2, 3, 2, which was about right here. There was something interesting happening there. At 5, 0, which is here, That was one of the endpoints, and then 1, 4, which was this one. So remember how I tilted it over and we could see the parabola? We found that top peak of the parabola right there, and that corresponds to this one, right?
Yep.
But that doesn't turn out to be, well, it might turn out to be a max. We'll see. We have to keep going. We still need to go along L3. All right, L3. So what's nice about L3? Yeah, it's a vertical line. So the x-coordinate is 0, isn't it?
1.
Yeah, sorry, 1, yes, thank you. 1, and then the y-coordinate, what's the y-coordinate? It's whatever y is, right? It's y. And if we're going to be moving, so any point along here, the x is 1, the y is between 1 and 4. So we have a different variable now. We have y instead of x. Big deal, right? It's still going to turn out to be a function of one variable. So now we look at our original surface, and we look at it at 1y, which will be replacing all of our x's with 1 and leave our y's alone. So we should get 3 plus y minus 1 minus 2y. Right? This turns out to be 2 minus y. Now, how comfortable are you all with this idea? I'm supposed to go and make this a function of one variable now, which it is, right? And then look at the closed interval 1, 4 and take the derivative, set it to 0, and do all that, right? But how comfortable are you with the idea that I don't need to take the derivative? Why don't I need to take derivative of that? It would be a constant, right? Which would never be 0. In other words, if we know this is a line, right? It's linear. When you have something that's linear, you're never going to have like a hump or something in it. So you're always only going to need to look at the two endpoints. So because this is linear, I can just kind of skip to the idea of saying, okay, I just need to look at what happens when this is 1 and the y is at the two extremes. So 1, 1 and 1, 4. Make sense? Okay, this, no critical points from this, all right? So we plug those in again and we see what we get. I believe we've done 1, 1, haven't we? When we did L1, didn't we have 1, 1?
Yeah, it was
Right, we did. And what was it? Didn't we? Did I say 1, 1?
No, you did 1, 0.
We did 1, 0. Wait, why am I putting 1, 1? Hold on a second. Oh, I see why. Look, everyone. This is 0 to 4. Why didn't anyone tell me that? 0 to 4. Right? Because, look, y goes between 0 and 4.
Yeah.
Okay, so that means this one should be 0. Sorry, we did 1, 0, didn't we? What was f of 1, 0? 2. And then f of 1, 4, we did that already over there, right? We already did that one. So there's a little bit of overlap at where the lines are intersecting one another. So I already know that's -2. All right. We are ready to draw a conclusion. What is the absolute maximum of this surface or this function on that triangle? The absolute maximum value is 2. Now, it occurs at multiple places, doesn't it?
Yes, it does.
Okay. What is the absolute minimum?
-2.
-2. And that also occurs at several places?
Yes.
Yes.
Okay. So in this, I'm not as interested in knowing where it happens, just what the value is.
So where it happens would just be
The xy along with those z's. Now I'm going to bring up the picture so we can see it. Let me get some of this crap out of here. This out. The region I want, here are my points. So you can see here that our absolute minimum was -2, and you can see it happens at these 2 points. And then our absolute maximum happened along, well, that corner point down here at 1, 0. And then the other absolute max occurred along this L2 at that peak of the parabola. So this is a little more involved, would you agree, than the previous one? Because you have to work your way around. And that was just a triangle. There's nothing that says it has to be a triangle. It could be some arbitrary shape. So here's another one. Find the absolute maximum and minimum values of this function on the rectangle d equals. So this is a type of notation we use. We're saying d is the set of all points where x is between 0 and 3, including 0 and 3, and y is between 0 and 2, including 0 and including 2. So that is a rectangle. Okay, it's all the points where your x value is between 0 and 3. Okay, all points between here and here, and our y's are between 0 and 2. So between here and here. So that creates this closed bounded region, right? So imagine taking those and plugging just those into this function. There it is on the ground. Here's our surface. We're just going to plug those points from there in, which gives us this region. I'll take the surface out again. So we're looking for the max and mins of that green sheet. And so, yeah, we need to go L1, L2, L3. I don't know why that thing shrunk over there. L3 and L4. We got to move all the way around.
Can you zoom in a little bit? It's kind of hard to tell.
That was for Danny. She can read that. Can you just ask her, please, what that says? All right, should we do it? Yeah? Okay. Tedious, right? This is tedious.
So you first probably need to graph it on the 2D, start graphing on 2D surface so you can figure out the layout of the rectangle?
Yes, but before you do that, what goes before that? Yeah, don't forget you have to look on the inside of it first. Before you start working around the boundary, you got to look at the inside first. And to look at the inside, that's where we do partial of f with respect to x equals 0, partial of f with respect to y equals 0. Now in the previous problem, when we did that, didn't we get the point 2, 1? And when we plugged it in, we got 1 as an answer, right? It was 2, 1, 1. And so we threw it out because our max was 2 and our min was -2. It could have been, though, that at 2, 1, it could have come out to be like 10, and then that would have been our absolute max. But we have to do the inside. So let's do these. Partial of f with respect to x is 2x minus 2y equals 0. And then the partial of f with respect to y, -2x plus 2 equals 0. Right?
Yes.
And that, I think, again, is going to be pretty straightforward because the second equation has a unique solution to it. Right? X is 1. Once I know that x is 1, I can go back up to this one. I think we get y is 1, right? So do I need to show that work, or are y'all okay with that? X is 1, y is 1 makes that true and that true at the same time. Do I need to show it or not? No? Okay. And so now if we want to know what the function's value is here, oh wait, we need to make sure it's in our rectangle. Is it in our rectangle? Yeah, it's in here. Here's 3, here's 2. Okay, so 1, 1 is in here. So that may turn out to be where we have a max, but We need to evaluate the function there. I'm going to put it off to the side. What is f11? Is it just 1? Looks like just 1, right? So when we plug in 1, 1, we get 1 to the original function. What is nice about this rectangle? What's going to be nice when we move along? They're all straight lines, right? That one of the variables is going to be constant, right? It's not like that diagonal we had a little while ago where it was x, negative x plus 5. That's not going to happen here. So let's start going here. L1, L2, L3. Don't ask me why I'm going counterclockwise. I really don't have a reason. So L1, what do all points on L1 look like? X0. And what's our x bounded between? 0 to 3, right? Let's just set up all the L1, 2, 3, and 4. I don't think I'm actually going to go through all of these. L2 would look like what? 3y, where my y is between 0 to 2. So my y is allowed to go between 0 and 2, but my x is fixed at 3. At L3, which is up here, x2, and x is between 0 and 3. So my x's can float between 0 and 3, but my y has to be fixed at 2. And then lastly, on L4, my x is fixed at 0, and my y is not fixed, but my y floats between 0 and 2. So x is 0, y goes between 0 and 2. And then we have to take each of these, right? This, plug it in there, figure out what we're looking at, find the max and min on a closed interval. This, same thing, same thing, same thing. I believe in the notes, if I'm not mistaken, all of this is done for you. Like I do it here. Like, where's the first one? X0. On L1, we have points x0 where x is between 0 and 3. Therefore, when we plug it into the function, blah, 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 we get this parabola. And then we take the, do the cal1, take the derivative, set it to 0, and I do that for each of the L1, 2, 3, and 4. So I think I'll let you mess with that. Let's see if there's something a little more interesting than this. Ah, okay, this one's a more interesting one. We have this surface, xy squared, but look at our region. Our region is that x is bigger than 0. That's a weird way to write it, but that means x is bigger than 0, and y is bigger than 0, and x squared plus y squared is less than or equal to 3.
Wouldn't it just mean that x is moved from 0 to x is square root of 3?
So we have to be in the first quadrant, right? And what is x squared plus y squared equals 3? What would that be? What would, if this was an equal sign, that would be circle with radius square root of 3, right? But I want that everything less than or equal to it. So it's like just in the first quadrant, root 3 here, root 3 here, right? This is our region. So we're taking just the points in there, mapping them up into this surface. Here's our surface. Here's our domain. Here's our domain on the ground. Here's our surface. Here's the surface just restricted to our domain. Let me pull the surface out again. And so I'm trying to find the, or we're trying to find the max, absolute max and min of that green weird looking thing, right? All right, so I think we should set this one up and maybe go through it because this is going to be a little bit harder in terms of our moving around. But what must we do first? Look on the inside. Look on the inside. So how do we look on the inside? partial with respect to x equals 0, partial with respect to y equals 0. So what's partial with respect to x? Y squared, and set that to 0, and there's only one answer to that. And then partial with respect to y is 2xy, right? Equals 0. Ooh, this is interesting. Okay, this has not happened. Yeah, so look, the first one, we get one answer and one answer only, right? Y must be 0. And if y is 0, then this equation is always true, regardless of x, isn't it? So that means the solutions to this, to make these two true simultaneously, means that we can use any x value we want as long as our y value is 0, and that would work, right? There's an infinite number of points here. However, what do all these points look like when you know, like what are they? They all live on the same line, don't they? They're all on the x-axis, which happens to be part of this, right? Yes. But also out there and out this way. So let's just see, what does our function look like? What does the original function look like if we're on one of those? On any point that's on the x-axis, our function looks like what? 0, right? You plug in y is 0, you get 0. So that means that could be a minimum, could be a maximum, just depends. We need to go compare. But anywhere along the x-axis, we're going to have 0 come out, right? All right, we're going to back burner that. We'll come back to that. Let's start to label some things here. L1, curve 1, circle 1, L2. Let's move along L1. All points look like x0. X is between 0 and what? Root 3. Okay, what does our original function look like at any of these points? We already know. We already did this, right? Just 0. There's no more work to do. We know that when we plug in any point that looks like this, regardless of what x is, the value of the function is 0. So along this edge, everything is 0. Beautiful. Great. Okay? Let's do L2 now. I'm going to skip C1. On L2, all my points look like what? So if you're on L2, the x-coordinate is 0 and the y-coordinate is y, and y is between 0 and root 3. So your y can float up and down, but your x has to be fixed. What's good about that, though? Every point, when you plug those points into the original function, now your x is 0, and it's still 0. So along that edge, your function's still flat. So the only thing interesting happening is what's happening along C1. So let's move along C1. So if you were on C1, what does an arbitrary point on C1 look like?
Looks like part of a unit circle.
Okay, well, if it's root 3, so it's not unit, but
It's not the right unit.
when it was a line, didn't we do x and then it was like negative x plus 5? You found the equation of the line, didn't you? Well, let's do the same thing here. What's the equation of that part of the circle? Yeah, we take this equation of the circle, right? Right there. We solve it for y. When we solve, that was given to us, right? Right here. Solve that for y, and you'll get plus or minus the square root of 3 minus x squared, right? That's what you would get. Now, it can't be both. It can't be both plus and minus. But it's your y-coordinate, and we're up in the above the x-axis, so it can't be the negative. So we'll chunk the negative. It's the positive, right? So what do all points on C1 look like then? X is just x, right? And then the y is root 3 minus x squared. So same thing, we're trying to get an idea of what every ordered pair on that curve looks like. And restrictions, do we have any restrictions on this x?
0,
0 to root 3. And now we need to go and plug this into the function to see what it would look like. Okay, so what happens? X stays X, and the Y is squared. So I square this, right? And that's really nice, isn't it? Isn't it nice to see that? Because when you square that, it kills off the square root. And that's going to keep us here at a nice polynomial. And we don't mind taking derivatives of polynomials. So 3x minus x cubed. What now? Take the derivative of that, right? So we need to do the critical points. So I'm gonna use a slightly different notation. Instead of calling this g or h or something, I'm just going to do this. I want the derivative of that function, right? I want the derivative of that function, which is 3 minus 3x squared. And then you set that equal to 0, right? So if I set that to 0, what are my solutions? So if I set that derivative equal to 0, my solutions are x is 1 and negative 1. So I trust that you could solve that, right? And one of those solutions I'm going to throw out, negative 1, because negative 1 is over here, and I'm only in here. So x is 1 is the only important place. And so now what I need to do is to evaluate this function, at my endpoints. So let's do that. Let's do it right here first. If x is 1, what's the y coordinate? If x is 1, the y coordinate is going to be root 2, right? Then we have to do the function evaluated at 0 and root 3. So what happens if we get 0 in there? Sorry, we'll just do it this way. This will be 0 root 3, and then question mark, and then the last one would be f of root 3, 0, whatever that is. All right, so I'm hoping you understand at least the setup on that and where everything comes from. The work for this is, again, below this. All right. Okay, I hate to end class early. We still have an hour, but I think you were all kind of probably at that point where we've done enough. Do you feel that way for today? Mm-hmm. Okay, so what will be on the exam will be everything up until the section right before this. So I'm not going to ask you anything on closed bounded sets. Okay. All right? So today we talked about two different things. Max, local min, which was capital D, right? Yes. And then we transitioned into closed bounded sets, which was moving around and doing the moving around stuff, not on the exam on Monday. All right? We'll postpone. Open bounded sets on the exam Monday? Yes, that capital D will be on the test. Okay? So now let me bring up a couple of my old tests here, and I'll just kind of talk to you about the types of questions that I asked. I will record this, and I am unmuted and everything else, but if you want to jot something down, you can. Since this is our first test, what I'm going to do is I'll write up the test. I'll take the test. I'll see how long it takes me. I usually multiply that by 6, and then I see like how much time that is. And then I'll give you that amount of time. So next class, I do plan on talking about the next thing, but it's going to be weird because you're going to be not wanting to do that, right? You're going to want to come in and like get the test done, and then after that you're not going to want to sit around and do lecture. And if I lecture before the test, you're not going to care what I'm saying because you're about to take a test. So it's one of those weird things. We've bought ourselves some time, right? We did kind of buy ourselves some time, but on the schedule, we are, so if we just come in on Monday and just take the test, then we will be right where we're supposed to be in the class. Like, we won't be ahead anymore, which is okay with me, but you know. I don't think we can move as fast now. Now things get a little bit too dense to move quickly, but it's all right. We'll figure it out. So do y'all like that idea of just coming in and testing? And then what I'll do is, like I said, I'll take the test and then I'll multiply by 8, and that's how much time I'll give you. So you may not get the whole time. You may not get the whole class period, just because there is a part of this that is about how efficient are you. Like, if it's going to take you 30 minutes to take a derivative of a polynomial, then, you know, that's a problem. So, all right, yeah, so let's talk about the test. I have not made the test, all right? So don't ask me how many questions, because I'm not sure yet. But I do have some old tests here to look at. Oh, this thing is about to die. Hold on. If it dies and that's it, I guess you don't get to hear what's on the test. There we go. I think I'm just going to sit down over here and talk. All right. You ready? Things that I have asked in the past. Finding the vector equation of a line. However, it's not as obvious as that. I may say find the vector equation of the line of intersection of two planes. It may be find the vector equation of the line that is perpendicular to this plane and passes through this point. You know, there were some problems that were kind of messy, and I did show you a list of them in class. Do you remember that list I went through? So these are those types of problems that you should be able to do. Okay. I would expect to see like 2 of those, all right? Within that, well, not within that, separate problems, shortest distances between either 2 planes or like a point and a line. So when we were doing distances, there were 2 formulas, one for shortest distance between a point and a line, and the other one was shortest distance between a point and a plane. So I would be comfortable using those formulas. And I'll talk to you about what you can bring to the test after we finish this. Finding the vector equation of a line that's tangent to a curve. So I give you a vector function, which is some curve, and I ask you to find the vector equation of the tangent line. So that's when we started taking derivatives of vector functions. If I give you a position function, can you give me the velocity and acceleration function? On the other hand, if I give you an acceleration function, can you go backwards and give me velocity and position? Can you find the length of a curve? If I give you a vector function, can you tell me how long that curve is on some... And that can be tricky, because when I give you a function and I ask you for the length of the curve, I can give you like between t equals, let's say, this time and this time, or I could give you just the 2 endpoints. Then you have to figure out what t is, right, to find your 2 ends. So calculating the curvature of something. Remember, there were 2 formulas. Sometimes one was better than the other. Okay. Continuing. showing a limit doesn't exist. Now, I'm not saying that this is going to be like this many problems on the test. I'm just trying to give you a flavor of things I've asked in the past. There may be something you study for that you don't even see on the test, and that just sucks. That's the way it is. All right? So I give you a function, and I ask you to show a limit does not exist. And so you've got to come in from different ways until you can get two different answers. Use a chain rule for something. So that's where I want you to make a tree and figure out a derivative. That was last class. Find the directional derivative. So I give you a function, I give you a point, I give you a vector, not necessarily a unit vector, but I give you a vector, and then you use the formula for directional derivative. Find the equation of the plane that is tangent to a surface. And we did that last class. We started class where we found the equation of a tangent plane to a surface that had to be a function of two variables. And at the end of class, we found the equation of a plane of just an arbitrary surface. So there was two formulas depending on what you're handed. In this particular test, it was the second formula because I gave them something that looks like, it's not even quadratic, but it would be like an ellipsoid. It's not a surface, so to speak, of a function of two variables. All right, and then we finally get to things that sound somewhat familiar to today. Find the extreme values, saddle points, etc., of the following surface. Ask for the answer as an ordered triple, so I want the x, y, and z coordinates. So that's what we did at the beginning. And then the next one was absolute max and min on a bounded region, so that's not on there, so you don't need to worry about that. Sounds like pretty much everything we've done. I mean, there's not a lot of vector stuff on there, right? Like I'm not going to give you like two vectors and ask you for a cross product, right? I mean, that's pretty obvious. But somewhere within the test, you're going to do a cross product, right? It's gonna happen somewhere. So what I'm going to allow you, and this is where things philosophically get very different. They're very different, school to school, professor to professor, different philosophies. And I think I alluded to this in the beginning. I'm one of those people that don't believe that you'll ever be trapped in a room by yourself with no resources. And in the real world, that's not the way it is, unless it's like Apollo 13 and you're up there trapped in a capsule and all you got's what's in there, So, well, even then, right, they had radio communication. So, I mean, they had someone to go to. Right, y'all know what I'm talking about? You've seen that movie, right? Yeah. Where they had to figure out how they were going to get rid of all the, filter their air, right? You think they would have figured that out on their own?
Well, the people on the ground did it.
That's right. But yeah, so I mean, even them trapped up there, they had someone to call on, right? Yeah. So you are allowed to have any formulas that are in Canvas in our folder. There's a folder that says formulas you can have for your test. You can bring any of those, all of those. You don't need them all because we haven't even covered some of them. And then you can have one additional page that you create for yourself. Now that page cannot have worked out problems. All right, you can't just work out a bunch of examples and have that. You can write, I'm not going to give you the formula for shortest distance between a point and a plane. I'm not going to give that to you, so I would put that there. I'm not going to give you the formula for arc length, so I would put that there. So run through the things that you've done. Anything that's not on the formulas that I've provided you, make sure you have that written down. You may give yourself steps and procedures, hints, as long as it's not worked out. So if you want to say remember to find the line of intersection of two planes, you cross the two normals to get your direction vector, then solve a system of equations to get any arbitrary point on the line. You can write those steps out for yourself, but you just can't have a problem worked out. All right? Front and back, standard sheet of paper. If Danny could probably put, I'm just going to keep picking on you, I'm sorry. Right, like an encyclopedia on there, but I don't care.